So far this week, you've learned some fundamental principles of how battery cells are constructed and how they work, how they produce a voltage, and how we might consider designing them from elements in the periodic table. Now we start the last substantive lesson of the week, where we summarize a lot of what you've learned already by looking at 3 individual examples of electrochemical battery cells. We start with one that's very commonly found in introductory textbooks on electrochemistry, and this is called a Daniell cell. It's probably the easiest and the simplest to understand, and so it gives us a good starting point for our example. Each half cell in the Daniell cell consists of a solid metal electrode submerged into an electrolyte solution. The negative electrode is made from solid zinc, and the electrolyte in the negative electrode region is zinc sulfate, which disassociates into positively charged zinc ions plus negatively charged sulfate ions when dissolved in water. The positive electrode is made from solid copper. The electrolyte in the positive electrode region is copper sulfate, which dissociates into positively charged copper ions and negatively charged sulfate ions when dissolved in water. The figure on the right-hand side of the slide shows a schematic of a Daniell cell. It has all of the components that I've already mentioned, and it also shows the separator, which is made from some kind of a porous ceramic disc that allows the negatively charged sulfate anions to move back and forth from one side of the Daniell cell to the other. When the Daniell cell is being discharged, zinc from the zinc anode gives up 2 electrons to the external circuit, and it also gives up a positively charged zinc ion into the electrolyte. The positive electrode receives the electrons from the external circuit, and it consumes positively charged copper ions from the electrolyte in order to copper plate the surface of the copper electrode. Because a zinc cation is being produced at the negative electrode, there will be a local net positive charge in the electrolyte there at that point in time. And similarly, because copper cations are being removed from the electrolyte in the positive electrode, there will be a local net negative charge in that region. So this difference in charge at local points in the cell cause the negatively charged sulfate ions to migrate from one side of the Daniell cell to the other through the porous disc in the center of this cell. And when we're charging a Daniell cell, exactly the opposite happens. So that is, copper dissolves from the positive electrode into the electrolyte, and zinc plates onto the negative electrode, and electrons pass through the external circuit in the opposite direction as they are forced to do so by some electronic charging means. If we go to a table of electrochemical series, we can look up the half reactions that occur in each one of the electrode regions. We find that in the negative electrode we have a redox reaction of zinc 2+ combined with 2 electrons becomes zinc metal, and that this half reaction has a standard potential of negative 0.76 volts. In the positive electrode, we have a redox reaction of copper 2+ combining with 2 electrons to become copper solid, and this reaction has a standard potential of 0.34 volts. So the overall reaction by combining the reactions in the 2 half cells is that zinc combined with copper becomes zinc 2+ combined with copper, as we see here. The overall reaction has standard potential computed as the standard potential of the positive electrode minus the standard potential of the negative electrode, or in other words, 0.34 volts minus negative 0.76 volts, which gives the sum of 1.1 volt for the Daniell cell. We note that the standard potentials listed in the electrochemical series assume what are known as standard conditions, which has to do with a specified electrolyte concentration and specified temperatures and so forth. So in practice, you will find that the actual voltage of a particular Daniell cell will vary somewhat from the standard potential that we have listed here in practice. And in particular, the voltage will be somewhat higher when the cell is fully charged, and it will be somewhat lower when the cell is discharged. We now start to look at our second example, which is a lead-acid battery cell. Both electrodes in a lead-acid battery cell are made from some metallic lead-based plates, and the electrolyte is sulfuric acid in an aqueous solution, in other words, dissolved in water. When a lead-acid cell is fully discharged, then both electrodes are lead sulfate, and the electrolyte is a dilute solution of sulfuric acid. If, however, the lead-acid cell holds some charge, and we are in the process of discharging this cell, the negative electrode reaction is listed as shown. We see that solid lead combined with a sulfate anion becomes lead sulfate plus 2 electrons. We also see that the positive electrode reaction has lead oxide in solid form combining with sulfate anions plus protons from the external circuit to form lead sulfate plus water. When we combine the two half reactions, the total reaction is lead plus lead oxide plus sulfuric acid becomes lead sulfate plus water in liquid form. And the opposite reaction occurs when charging a lead-acid battery cell. When fully recharged, the negative electrode is solid lead and the positive electrode is solid lead oxide, and the electrolyte is a more concentrated solution of sulfuric acid. The standard potential of the reaction that happens in the negative electrode is negative 0.356 volts, and the standard potential of the reaction that happens in the positive electrode is 1.685 volts. So when we combine these two values together, we find that a lead-acid cell has standard potential of 1.685 volts minus negative 0.356 volts, which comes out to 2.041 volts. Again, the voltage of a lead-acid cell will vary with the concentration of the sulfuric acid. In fact, it's possible to measure the concentration of the sulfuric acid and use that as an indicator of the state of charge of the battery cell. We also find that the voltage changes with temperature, so we sometimes see slightly different values listed as the nominal potential of a lead-acid battery cell in the literature, but these values are almost always between 2.0 volts and 2.1 volts. Again, we note that vehicle lead-acid batteries, also known as 12-volt batteries, are built from 6 individual lead-acid cells packaged in series in a single container. And similarly, some motorcycle batteries are 6-volt batteries that comprise 3 individual lead-acid cells internally wired in series. When we charge a lead-acid battery, it's important to protect against overcharge. If we overcharge a lead-acid battery, then water in the electrolyte will decompose into hydrogen and oxygen gases. Under some circumstances, other compounds in the electrodes can be electrolyzed as well to create poisonous gases, and all of these gases can cause bulging and deformation of sealed lead-acid batteries. It's also important to protect a lead-acid battery against over-discharge. If we discharge a lead-acid battery too far, then lead sulfate crystals will form, and these crystals often cannot be decomposed, which means that we lose some of the lead that could otherwise be cycled back and forth in our battery cell, and therefore some capacity of the battery cell is permanently lost. So if you were designing a battery management system for a lead-acid battery, it's important to limit the depth of discharge. Also note that lead-acid batteries have a property that's somewhat unusual. It's possible to trickle charge a lead-acid battery cell. That means that when the cell is fully charged, we can hold the terminals of this cell at a fully charged voltage, which continuously forces a very small amount of current to continue to flow into the cell and through this cell. The water in the electrolyte at this full charge point decomposes into hydrogen and oxygen gases, but if the trickle charge is at a slow enough rate, these gases then can recombine back into water at the same rate. So I form gases and then I form water again at an equilibrium rate overall. And so By doing this trickle charging or float charging, the battery cell is maintained in a fully charged state while not causing any permanent damage while we're doing so. And this counteracts some natural self-discharge processes that would otherwise cause the battery cell to slowly discharge over time, leading to the problem that we just talked about of lead sulfate crystals forming. If a lead-acid battery cell does happen to over-discharge, in some cases it's possible to use pulses of current to break up the lead dioxide crystals and to restore some of the capacity. And this is a feature in many battery management systems and chargers for lead-acid battery cells. Also notice that this trickle charge that I mentioned can be used to equalize battery cells when they're connected in series at a top state of charge point. That is, if the cells have slightly different characteristics, one cell may reach a fully charged point before the other cells in the battery pack reach that point. And if I stop charging when the top cell has reached the top state of charge, then my overall battery pack is not balanced, it's not equalized, and not all cells in the battery are holding as much energy as they could. But because it's possible to trickle charge a lead-acid battery, if I continue to charge when one cell is at the top, it simply remains at the top and the other cells slowly come up and balance with that top cell. And so trickle charge is very practical, very important in a lead-acid battery cell. And you're going to find out that next week, when we look at lithium-ion battery cells, that we cannot do trickle charging with lithium-ion battery cells because they are too efficient and they will just keep on charging forever and ever until they catch fire and explode. And of course, we have to avoid that. So the trickle charging in a lead-acid cell allows cells that are already fully charged to remain in that state, while the remaining cells in the battery continue to charge until all cells are fully charged. Now, lead-acid battery chemistry was invented more than 150 years ago, so the technology is very mature. Even so, there are some variations in how lead-acid battery cells are constructed depending on the application for which the battery will be used. For example, the lead-acid batteries are not usually built using solid lead plates like you might think at first. Instead, the electrodes are usually constructed from some kind of a grid that looks a little bit like the screen mesh you would put over a window in your house or over some doorway to keep the insects from flying in. And this grid is made from a lead alloy for strength, but it's covered with a sponge-like lead paste, which is the actual electrode material. And this is done for a very interesting reason. If we simply used lead plates for the electrodes of the battery, then the surface area of the lead plate over which the charge and discharge reactions occur is simply equal to the length of the plate by the width of the plate, and maybe multiplied by 2 if we're using both sides of the plate. The interior of the plate does not participate in the reaction, it's only the surface, and so the surface area is what matters. If we use a sponge-like substance instead, then there can be enormous surface area due to all of the holes and the porous nature of the sponge. And the discharge and charge reactions can happen over the entire surface area, including all the surface inside of the sponge-like material, which means that if I'm limited in how fast a reaction happens per square meter, if I increase the number of square meters of electrode, then I increase the rate at which we can charge and discharge a lead-acid battery cell. So fundamentally, this means we can get much more power out of a battery cell that uses these sponge-like electrodes because power is the rate at which energy can be added and removed. Some types of lead-acid battery cells are called flooded cells, and in flooded cells the separator is just a mechanical spacer and the electrolyte is liquid sulfuric acid, but flooded cells are relatively uncommon anymore. Another type of lead-acid cell is called an absorptive glass mat, or an AGM cell. In these cells, the separator is a porous material made from glass fibers that forms a mat that is saturated with a minimal amount of electrolyte. These AGM cells, because they use a very small amount of electrolyte, do not create large volumes of gases when they're overcharged. And so the cell can have a sealed construction instead of a vented construction, and it makes the cell maintenance free, which can be a huge advantage in a lot of applications. And sometimes silica is added to the electrolyte to turn the liquid electrolyte into more of a gel. And this also allows for a sealed construction, and it allows for less variation in the concentration of the sulfuric acid at different parts in the cell. You see, if I had a purely liquid electrolyte, the electrolyte tends to stratify with higher concentrations in one part and lower concentrations in another, and this causes the aging of the cell to vary depending on whether you're at the bottom of the cell or at the top of the cell. And by adding the silica, you can actually improve life by making aging more uniform. When we add the silica and create this gel, the resulting lead-acid battery is often called a gel cell because of that. So when we make this gel cell, we often have longer life, but also the trade-off is we often also have lower power because the electrolyte has a higher ionic resistance than the liquid electrolyte. Our third and final example for this lesson is nickel metal hydride battery cells, and these are really interesting. The principle of operation for a nickel metal hydride cell is quite different from what we've seen already this week. Metal hydride cells depend on the ability of some metallic alloys known as hydrides to absorb large amounts of hydrogen like a sponge absorbs water. So it absorbs this hydrogen in pores in the metallic material. Now, hydrogen can decompose into an electron and a proton, and so hydrogen can be used as the charge carrier inside of a battery cell. So if an electrode has the ability to absorb hydrogen and release hydrogen as separate protons and electrons, then it can act as a negative electrode. And you're going to learn next week that lithium-ion cells work in a very similar way to this, except that in that case both electrodes work in such a way that lithium is absorbed into the electrodes a lot like water is absorbed into a sponge, instead of performing a standard redox electrochemical reaction at the surface of the electrode. So metal hydride cells use these metal alloys and their negative electrodes, and they use a nickel hydroxide as the positive electrode. And the distinction between what's happening in the negative electrode versus what's happening in a standard traditional redox reaction is that we don't really have a standard electrochemical redox reaction happening in the negative electrode at all. We're simply taking the proton from the electrolyte and the electron from the external circuit, combining them into an uncharged hydrogen that gets absorbed in this material when we're charging the electrode, and when we're discharging, the opposite happens. So no standard chemical reaction takes place that could deform the electrode. We're not causing products to build up at the surface or to be removed at the surface. Instead, hydrogen simply goes into the electrode and comes out of the electrode. And this is why metal hydride cells often have much, much longer lives than a standard electrochemical battery cell. And as I mentioned a minute ago, lithium-ion cells work in a very similar way, which is why lithium-ion battery cells tend to have much, much longer lives than standard rechargeable cells do. Inside a metal hydride battery cell, the electrolyte is some kind of a hydrogen-absorbent aqueous solution, such as potassium hydroxide, and it really takes no part in the chemical reaction at all. It simply serves as a way to transport the hydrogen ions, the protons, between the electrodes. So the magic, if you want to think of it that way, of a nickel metal hydride battery cell is how the negative electrode works. The electrode is some kind of a rare earth hydrogen absorbing metal alloy, and there can be different structures used. For example, a structure in an AB5 format where A can be lanthanum or cerium or neodymium or praseodymium, and the B can be nickel or cobalt or manganese or aluminum. Or the structure in some cases has an AB2 form where A can be titanium or vanadium and B can be zirconium or nickel doped with chromium or cobalt or iron or manganese. These details are not at all the focus of the course, but it's interesting to think about how the electrode structure is built. The key point is that hydrogen is absorbed into this metal alloy without changing its chemical formulation in any way, and more importantly, without changing its physical structure. And the picture on the right shows an example of what I mean. The dark-colored spheres indicate atoms in this metal hydride alloy, and the gray-colored spheres indicate hydrogen atoms. These hydrogen atoms can fit into the vacancies, into the openings in the crystal structure of the metal alloy without changing its chemical composition and without changing the structure in any way. And it's exactly like water absorbed in a sponge. I can take a dry sponge and I can place it in water and it absorbs the water, and then I can squeeze the sponge and the water goes back out. And at least ideally the sponge itself has not changed in any way by adding or removing the water. And if I allow the sponge to dry out on the counter, it retains exactly the same form that it had to begin with. So this mechanism by which hydrogen gets inserted into the electrode, which is called intercalation, and the mechanism by which it is removed from the electrode, which is called deintercalation, is very gentle when compared with a standard redox reaction, and so nickel metal hydride cells tend to have very long lives. We'd like to, for this example, also compute the voltage of a nickel metal hydride cell like we did for the other two battery chemistries. And so once again, we need to look up the standard potentials of the half reactions that occur in each electrode. In the negative electrode, we have M, which stands for the metal hydride, plus a proton plus an electron becomes the metal combined with hydrogen. The standard potential for this reaction depends on what we use for M, but it's generally around negative 0.8 volts. The positive electrode, which is nickel hydroxide, has a half reaction of nickel hydroxide plus hydroxide becomes nickel oxide hydroxide plus water plus an electron. And this half reaction has a standard potential of 0.5 volts. Therefore, the overall reaction is nickel hydroxide plus metal becomes nickel oxide hydroxide plus a metal combined with hydrogen, having a potential of 0.5 volts minus negative 0.8 volts, or around 1.3 volts. When charging a nickel metal hydroxide battery cell, we must again be careful to guard against overvoltage. If a nickel metal hydroxide cell is overcharged, then oxygen gas evolves when the positive electrode is no longer able to provide nickel hydroxide to react with the hydroxide in the electrolyte. But if a nickel metal hydroxide cell is charged very slowly, then oxygen gas can diffuse from one electrode to the other and combine safely with hydrogen to form water. So it actually is possible to slightly overcharge a nickel metal hydroxide battery cell a little bit if it's done, again, very slowly. And we must also guard against over-discharge when hydrogen gas is evolved. So to summarize this lesson, you have seen examples of three types of electrochemical battery cells: the Daniell cell, a lead-acid cell, and a nickel metal hydroxide cell. In each case, we investigated the individual half reactions that take place in the positive and negative electrodes, and from those, we're able to predict an overall cell nominal voltage. Despite the fact that these three cells have a lot of similarities, we also saw that there were some pretty significant distinctions between how they operated. The Daniell cell is unique in that it uses different electrolytes in the positive and negative electrodes. The lead-acid cell was unique in that it uses a sponge lead paste spread out over a lead alloy grid in order to increase the power that it can deliver. And the nickel metal hydroxide cell uses a hydrogen-absorbing metal hydride for its negative electrode, and this extends life. So while the battery management system algorithms that you will learn about in this specialization are quite general in nature, we are going to apply them specifically to lithium-ion battery cells, which have further distinctions from what you've learned about so far. So as we end this week and we start to turn our focus to what we will study next week, we're going to begin to look in particular at understanding how lithium-ion battery cells work in preparation to understand how to write algorithms to manage them properly.